I'm going to move on to the last major topic in chapter 9, which is osmosis. So I hope you like my picture here. I don't know if any of you tried this back in high school, right? This is what people used to say: if you sleep with your head on the book, the knowledge will transfer to your brain through osmosis overnight, right? I would love to know if any of you have tried this. But that is not really what osmosis is in the world of chemistry. So what is osmosis? The definition we're going to give you here is it's the passage of solvent. Okay, now I have capitalized that, I have underlined it, because it is not the passage of solute particles, and that's what your mind is going to want to tell you. But it is the passage of solvent particles through a semi-permeable membrane. Now, what does that word semi-permeable mean? Semi means some, okay? Something that is permeable means things can pass through it, okay? It's kind of like a filter of sorts. Semi-permeable means that some things can pass through, other things cannot, okay? So it's a selective filter, okay? Some things can pass through, some things cannot. Usually smaller things can pass through, larger things cannot. Okay, but let's finish the definition. The passage of solvent through a semi-permeable membrane, which is separating two solutions of different concentration. This is key, because what happens when you have two solutions with different concentrations separated by a semi-permeable membrane is we have what is known as a gradient. Okay, a gradient is where things such as solvent particles, some kind of particles, are going to want to move from one side to the other to make things even, okay? If we have different concentrations on each side of the membrane, the solvent is going to be forced to move because there's a gradient from areas of low concentration to areas of high concentration, okay? So in a gradient, solvent always moves from areas of, I don't know what I said earlier, but it should be areas of low concentration to high concentration. I hope that's what I said earlier. I can't remember if I said it right or not, but this is the correct answer. Gradient forces solvent to move from areas of low concentration to areas of high concentration, okay? All right, the next thing we read is that osmosis depends on the concentration of each particle. So we do not care about the particle identity. We really only care about concentration when it comes to this idea of osmosis, okay? So don't get lost in what kind of particles, and that's why, honestly, I've represented particles here as these red spheres. We're only going to be looking at how many red spheres. We don't care if it's sodium or chloride or what. But to define osmolarity, which is a unit as well of concentration, so this is another unit of concentration, or a term of concentration, I should say. What is osmolarity? It is equal to the moles of keyword particles, okay, per liter. Now, you guys are familiar with molarity, okay? So molarity, if you remember, in fact, I'm going to zoom in, is equal to moles of solute. I'm going to underline this word right here, solute, per liter of solution. Okay, we're familiar with molarity, and that's what molarity is. It's moles of solute. And I want you to think about solute for just a minute. Solute is a molecule, okay? So we're talking about moles of various molecules per liter of solution. And that is where osmolarity and molarity are different. Molarity, we're talking about moles of molecules. I know that sounds redundant to say, but a solute particle, or I should not say particle, a solute is a molecule, not a particle, okay? Solute equals molecule, not particle. This is like splitting hairs, I know, but it is a key difference here. that I wanted to point out. Okay, so you understand molarity, which should help you understand osmolarity, which is moles of particles. So the idea here is that sometimes molecules can break up into multiple particles or ions. All right, so we'll look at some examples of how to calculate osmolarity in a minute, but the definition of osmolarity is moles of particles per liter. Okay, if we're talking about if we have 1 molar sodium chloride, okay, you need to ask yourself how many moles of particles, or here a good word is ions, would I get? Okay, we can't always say ions because not every molecule dissolves into ions. But if a molecule does dissolve into ions, then it's broken down into smaller particles. Sodium chloride for sure dissolves into ions. Okay, we get 1 sodium cation, 1 chloride anion. So therefore, we will get 2 osmoles. Okay, 2 moles of particles per liter, that's 2 osmoles. If we have 1 molar glucose, it does not, kind of like what we were talking about with electrolytes earlier, it does not dissolve into ions or smaller particles. So if we have 1 mole of glucose molecules per liter, we have 1 mole of particles. Okay, glucose is the smallest particle that it will break down into. All right, so we call that 1 osmole. All right, moving on, if we had a setup like this, so this black line right here, I'm going to draw a pink line over it. This is our semi-permeable membrane, separating 2 solutions, and you'll see we've reported their concentration down here at the bottom in osmolarity. This side, if you count up all the red spheres, we have 15 red spheres, so we're going to say it's 3 times as concentrated as the right side of the semi-permeable membrane, which only has 5 red spheres. Okay, so we say it's 3 osmoles over here, 1 osmole over here, just to represent that this left side is 3 times more concentrated with the number of particles present than the right side. If osmosis were to occur, for the setup we have here, which way would the solvent particles move? Remember, let's go back and read up here. Due to this gradient, when you have a gradient difference, a difference in concentration, solvent moves from areas of low concentration to high concentration. So it's going to move from this side to this side. Okay, look, from the side of low concentration to the side of high concentration. Okay, because it's got to dilute the high concentration. The red spheres cannot move. They're the particles. It's only the water, the solute particles, that can move. Okay. All this stuff is what we had on the previous slide, so this is not new information. So let's look at what this saying is saying right here. So this is after osmosis has occurred. Now we have 2 solutions that we call isotonic, because after osmosis occurs, we have evened out the concentration. Okay, we've evened the osmolarity. Same osmolarity, which is same number of particles per liter. And we call a solution that has the same number of particles per liter isotonic, or 2 solutions, I should say, that have the same osmolarity or same number of particles per liter. Those are isotonic solutions. So now it looks like we have even concentration of particles. And so these 2 osmoles, showing you that we have the same osmolarity on both sides of our semi-permeable membrane right here. So these solutions, that's why it says, are isotonic. So you need to know what the term isotonic means. We're also going to introduce 2 other terms, hypertonic and hypotonic, in just a minute.